So I think it's time. Let's get started. For the benefit of our video audience, this recording is happening at C++ on C 2024, and we're in Folkestone, England, which is a beautiful and historic town sitting right on the cliffs of Dover, and I can literally see France right through that window right there. It's a beautiful sunny day. Speaking of the day, today is election day for our British hosts. For those of us who are Yanks, today is Independence Day. It's the 4th of July. So it is the 4th of July, 2024. No hard feelings. We've made up. This started with the treaty after the War of 1812. The treaty not only ended the war, it also resolved certain other important issues, like there were islands in the Great Lakes. We had to decide which were going to be Canadian and which were going to be U.S. And the U.S. was hosting this treaty. They were providing the venue and the catering and the maps and such. But the Canadians weren't involved. What it was is the king had sent negotiators to negotiate the treaty. And it turned out they were amazing negotiators. They were able to get all the big islands that were in the Great Lakes. And the Americans had to settle for, the Americans who had provided the maps had to settle for the islands that actually exist. All right. For those of you that are in the audience here, this is an audience participation talk. And when I ask a question, just go ahead and yell out the answer. That won't be hard. It's always the same answer. All right. So this talk is called "This is C++," and my assumption is that everyone here is familiar with C++. So we're not going to talk about details of C++. Instead, what I want to cover is this point of view of what is C++ for? What is C++ trying to accomplish, and how does it accomplish it? So understanding this is important for two reasons. The first is that we'll have a better idea of how best to use C++. And I think that's why we're all here today, is we want to use C++ better. And the second reason is it helps us to understand how C++ should evolve. Understanding what C++ is trying to accomplish guides us in discussing new language and library features. So in this talk, I'm going to explain what C++ is trying to accomplish, how it accomplishes it. I'll give some examples that illustrate this. Then I'll consider something that I consider one of the most important points of controversy that's facing C++ today, and how our understanding of C++ illuminates this controversy. Finally, I'll discuss the implications of this insight for one of the biggest challenges that's facing the community. So I want to answer the question, what is C++'s superpower? And before I tell you what I think the answer is, I want to explain that C++ has several superpowers, none of which are unique to C++. So what do you think C++ superpower is? Yeah.
I think it's a combination of performance and the high level of abstractions.
High level abstractions, expressivity.
And but the more behind the scenes is very efficient.
Yes. Do you have an idea?
Yes, it's a lot of paradigms.
A lot of paradigms are supported, right? Very flexible approaches. Anybody else?
Open standards.
Open standards. Okay, all right. So some people might suggest these are the ideas I already had: flexibility, portability, expressive power. And I'd say these are important, but at its root, C++ superpower is uncompromising performance. I think that is the superpower that we're addressing. When we try to design C++ to maximize flexibility, portability, expressiveness, safety, all these things, but never at the cost of performance. Why do we make this choice? Because this is C++. That's the choice we're making. Uncompromised performance, that's what it's about. When we're faced with a trade-off that gives us better safety at the cost of performance, we don't accept that. Why not? That's a question. What's the answer? Why not? Because this is C++. Exactly. All right. So members of the C++ Standards Committee understand that this is what is expected of C++, and that the definition of C++ can leave no room for a lower level language. What this means in practice is that although we may add various features that provide us with higher level abstractions, allowing us to reason about code at a higher level, very, very important and very valuable, we don't add features that violate our zero overhead rule. Now, some people misunderstand what this rule is. They think it means there can't be any overhead. That's not exactly what it means. It's a reasonable thing to go from the name. But the rule says that if a feature is not used, there's no overhead. If it is used, the feature has no overhead that exceeds or is greater than what would be required to implement the feature by hand. And as long as we stick by this rule, we can consistently maintain our uncompromised performance, right? All right, so how do we maintain that uncompromised performance? Well, there's a number of ways, but I'm going to focus on what I think is one of the key ones, which is that when we implement an instruction from the user's code, we implement it using machine instructions where that's possible. So we directly implement using machine instructions. So if the user's code is going to add 2 integers, we're going to use the machine instruction to add the 2 integers to accomplish that. If we're calling for division, we're going to use the machine instruction, if there is one on this platform, for integer division. We say, but wait a minute. Surely every language does that, right? Well, not necessarily. So let's look at these functions. In these functions, we've effectively done what I said, which is that each of these operations is effectively a single machine language instruction, right? The division is a single division. The multiplication is a single operation. But notice, all of these functions have safety concerns. What is the safety concern for our add function? What could go wrong? Overflow, that's right. And in fact, that's the same issue with mult, right? We could have integer overflow. Now, we don't have to worry about that for divide. What's the issue with divide? Divide by 0. Notice all of these are safety concerns that obviously the generated C++ code is not dealing with, right? Now, you could imagine a language where safety is a higher priority, performance is not the highest priority, that might do a different approach. So, for example, for division by 0, we might have something like division by 0 is defined to return the largest possible integer. It's as close to infinity as we can get, right? It's a reasonable thing. Or we could throw an exception. Or we could set some kind of error flag. Any of those kinds of things might be reasonably defined behaviors. But the issue is, with C++, we want the compiler to be able to generate code for most, ideally all platforms. And unless there's a bug in the hardware, all of these are going to yield the same results for the non-corner cases, for the common cases. But they might do different things for the corner cases, for those error conditions, those safety issues that I discussed, right? So what can we do? Well, what we could do is we could pick one particular behavior, and if that's not the behavior of the architecture that we're looking at, if it's not the native behavior, then we could emulate that, right? But the issue here is that in doing that, we would slow down not just the corner cases that are being emulated, but we would slow down the common cases. We'd be trading off on our uncompromised performance. And why is that? Well, in the case of division by 0, for example, you'd have to test the divisor on every division. So whether there's division by 0 or not, we're slowing down every division operation to be able to accommodate this, right? Okay, so let's take a look now at an attempt to do this. So here is, I've added div safe. And what does div safe do? Div safe does the simplest possible thing. It returns the max value of an integer, right? Okay, but look at our cost here, right? This is, as you can see, what's happening on the other side is it's about twice as many operations, and it includes a branch. And we know, of course, that branches are potentially performance killers. So we have created this new safe version of divide called div safe, but it is doing the simplest possible thing, and yet it is still, is increased our costs for using it. And so we don't take the safe option. And why don't we take the safe option? Because this is C++. That's right. That's exactly right. Now, someone might point out we don't always do this. So let's take a look at the vector class. It has an index operator. And what this does is it accesses a particular element and it does no range checking. But we also provide the at member. What does it do? Well, it does the same thing, except it does provide range checking. So this is actually a rare situation where we provide both. But which one is used more often? Is it close? Right? Right? I rarely see the at operator used in this context, right? And yet that's the safe option. If we were to provide, and I'm not saying we change anything, but I'm saying if we were to have only provided, if C++ only provided one option, which would we do? The safe option or the performance option? And why? Because this is C++. Exactly. You guys are catching right on. All right. Now, somebody could argue and say, wait a minute. This is a false feeling of better performance. Because if you're going to access elements of an array, or a vector, you absolutely need to make certain that you're in range. Accessing an element out of range is undefined behavior. So you need to know. And if we're not doing the checking in the library, all we've done is forced the library, or the caller, to have the same burden. We've just shifted the burden. It's no faster for the caller to do the check than for the library to do the check. So we're not really any faster. Of course, that's not really the case here. It's possible that the caller is going to make multiple accesses to an element. There could be multiple reads and writes to a particular element, so only one check would be necessary. But even more commonly, how do we access elements? It's almost always in a loop, right? And the loop can usually be set up in such a way that we are going to guarantee that we can't possibly be out of range. In that situation, no checking is required at all. We have set the loop up in such a way that we cannot be out of range. We cannot have unsafe behavior. And this is something that we can't, if that checking is done, we can't do this with the at member function because the at member function does the checking, right? So this leads us to the commonly made observation that you can build safe on top of fast, but you can't build fast on top of safe. And what do we mean by this? What we're saying is that if you have an API that does no domain checking, then you can build an API on top of that that does whatever checking is necessary to make it safe. But if you have an API that internally does domain testing, you can't take that away when it's unnecessary. You can't remove it when it's redundant. You cannot make a fast API on top of a safe API. You can make a safe API on top of a fast API, right? And this is the way not only C++ in the case of the index operator, but all through the C++ standard library, we have the same pattern repeated where the library does very minimal kinds of checking. Making it, the burden is on us as programmers, making it potentially unsafe if you don't write code that's proper. And why do we make that choice? Because this is C++. Great, okay. All right, so I believe that the superpower of C++, believe it or not, is undefined behavior. It's the fact that we put constraints on the code that we can write. That means that the code that we do write can be uncompromisingly fast. That is, believe it or not, it sounds like a terrible weakness. And when you teach C++ to students, of course, they freak out every time we talk about undefined behavior. But this is really a very powerful concept for us. Because what we've done is we've said, if you follow the rules, you're going to get great performance. what we do is we look at an operation and we say, is there any part of this operation that is going to be difficult to implement on all platforms in an uncompromising performance way? And if the answer is no, there are corner issues that might be dealt with differently, then we push those corner cases and say, we don't define what happens. Don't do that. Make that undefined behavior. And why do we take this approach? Because this is C++. Right. Okay, so I'm about to show you an example, and those of you that are tracking the standard development very closely are going to say, wait a minute, that's different for C++ 26. And I know that. Yes, C++ 26. There's an interesting proposal by Thomas, and I believe this has been accepted. If you can read that, and it actually changes what I'm about to tell you, but I'm going to tell you anyway because it's a great example, and the overall thrust of the example is still true, even though the details in this particular case are a little bit different. So I'm going to ask you to assume for the moment that we're only talking about C++ 23. Again, the details change in 26, but the overall import of what I'm telling you is the same. All right, so here's the example I want to give. We can write this code in C++. What is it doing? It's allowing us to declare something without giving an initial value. Now, naive users who've used other languages and come to C++, will often assume that there's an implicit initialization here that initializes to 0, right? That's not the case, but that's sometimes a surprise. Sometimes a surprise to naive users. I think experienced users know that won't be the case. How do we get to be experienced users? By making the wrong assumption in this case and learning the hard way, right? All right, so why don't we 0 initialize this? Well, it's because if we have a variable that we're going to assign a value to immediately that comes from the keyboard or comes from a file somewhere or comes from the network, then assigning an initial value before giving it the value we know, that's just waste of cycles, right? It's a compromise of our performance. And so we don't want to do that. We're not going to do that. Given a choice, now notice, by 0 initializing this, we would in fact have fewer bugs. I can pretty much guarantee you that right now, there's C++ code out there that has bugs because someone wrote code like this and made the assumption that there was actually initialization going on. Or perhaps they knew that this didn't initialize, but they end up with a code path that somehow doesn't initialize this before it's used. That bug is out there. And yet we accept that instead of initializing it. Why? Because this is C++. That's our approach. That's what we do. Now, this isn't the point of this talk, but I think the syntax for initializing could have been a little bit better. We could have had both ways. In other words, it would be nice if there was a syntax that would say, don't initialize this. And the default syntax does the initialization. That would be great. You could imagine something like this, right? Where this is saying, don't initialize this. But that ship has sailed. Now, notice also that, and I think, by the way, we have 50 years of system software experience, and we probably would have done something along this line. I think we learned that this was an unnecessarily unsafe approach. There needed to be a way to say, I want this uninitialized, but not have that happen by default. Okay, arguably that. We're not going to change this. By the way, this is a way of saying exactly this. This is legal, and what this means is, don't initialize this. This is legal. It's legal today, and that's what the compiler will generate, is uninitializing. And it's a way of telling someone reading the code that you didn't forget to initialize, you actually intentionally are leaving this uninitialized. Theoretically, this also works with user-defined types, but I wouldn't recommend you play with that because I don't think compilers necessarily do the right thing in those cases. So we won't push on that. And again, this is not really the point of this talk. Now, I would also go further, and I would say that you could imagine since using an uninitialized variable is undefined behavior, you could imagine that a future version of the language could say, oh no, this means to zero initialize. This syntax means to zero initialize. If we made that change, would we break any properly written code today? No, that would not be broken. Would we fix any bugs that are shipping today? Yes, absolutely would, right? But we don't do that, right? We're not taking the easy way out here. And why is that? We are deliberately making a choice that has bugs in the field as opposed to making a change that could fix those. Why? Because this is C++. Because it's all about uncompromising performance. Okay, I hit a wrong button somehow and my notes went away. So give me 1 second to see if I can get this back up. Sorry about that. Okay, all right. So I want to drill down a little bit on the safety issues around this uninitialized object. What is it we can legally do with an uninitialized object? What can we do? We can assign to it. That's correct, right? Can we read from it? Can we? Well, it has to have some value, right? We didn't initialize, but it's got to have some value. There's bits in the computer, right? It has to be, all right. So in theory, yes, but it is undefined behavior. So although you can say we can do it, but the language says we can't do it. That's undefined behavior. Reading this means that your hard drive gets formatted, demons fly out of your nose, whatever you want to use. All right. There's one other thing that we can do with an uninitialized object, and what is that?
As a parameter to something, so it can initialize it.
Yeah, but you haven't. I mean, you've passed it. You haven't done anything with it. I understand what you're saying, and that's technically true, but it's not the answer I'm looking for.
We read it as a pointer.
What's that?
We read it as a pointer.
Well, that's. I mean, that would be. Yes, you could cast it to something, but again, it's the same thing. We haven't really. What have we done with the thing? Right. What else can we do?
Destroy it.
Destroy it. That's right. We can do nothing with it. We can let it go out of scope. When it goes out of scope, it's destroyed. All right. Those are the two things that we can do with this. All right. Now I want to take a look at this function. So this function is taking an integer by reference and modifying that in place. Now, if you were writing documentation for this function, would you point out that the integer must be initialized? Would you have thought to include that in your documentation? Would you, if you were reading documentation for a function like this, would you look for that to be in there? Okay, I've had people in the audience that say, oh yes, in my company we would definitely have said that. Okay, that's great, but I think most people wouldn't, and the reason is, we pretty much assume if you're dealing with an integer, it's been initialized, right? It's pretty much an assumption. It's the way we would do. It is, of course, a requirement. If you don't do this, then all bets are off. If the integer comes in uninitialized. Now, in my day-to-day use of C++, I can't think of, I never create uninitialized objects. I don't really think about them very much, but they are part of the language. And so Alex Stepanoff and Paul McJones in Elements of Programming, they came up with a name for this. They call it a partially formed object. This is an object where the compiler knows the static type, but its runtime value is not fully formed. So the only things we can do with it is actually give it a value or just let it go out of scope, right? Now, the very existence of this in the language is a safety risk because this can be used incorrectly. And yet we have it in the language. Why is that? Again, because this is C++. So the analogy I want to use is like a ski slope. You have a well-groomed ski slope. If you stay in the defined path, you can ski at top speed. But you have to stay in the defined path. If you get on the edges, there's rocks and trees and crevasses and maybe cliffs, right? So we stay in the defined path and we ski at full speed. If we are coding using the defined behavior, that defined behavior has been defined because it means the compiler can generate code at uncompromised speed. That's what we're trying to accomplish, right? Now, the burden of this, the challenge of this, falls on us to make certain that our code is in the defined space. And that is a real burden. It is a real burden. You pretty much have to actually be awake when writing C++ code. There may be other languages where you can be half asleep, but you don't want to do that in C++. And why is that? Because this is C++. Great, great, great. All right. So I believe that undefined behavior is the power of C++. Because it allows us to push support for corner cases, that is, those undefined cases, onto the programmer. So the compiler can generate code that ignores those corner cases and yields uncompromised performance. Now, I want to briefly address something about undefined behavior that may be a surprise to naive users. And this issue arises from the fact that compiler writers don't actually think about undefined behavior the way we might naively expect. So a user that understands corner cases, understands that they're undefined behavior and why they're undefined behavior, might think about their situation as this. They say, well, I understand the platform that I'm writing on. I understand what its native behavior would be. And in my particular application, that's the behavior I want. So I don't have to worry about undefined behavior for this situation. In other words, let me give you a specific example. Suppose someone is on a platform and they know how the platform deals with integer overflow. And they say, okay, in my application, if integer overflow happens in that way, I'm good with that. That's the behavior I want. So I don't have to worry about the fact that there isn't actually a library guarantee or a language guarantee that says this is what will happen. And I can ignore that, right? You're shaking your head. You know better. Why is that? It's because that rests on a naive belief that the compiler writer is, when dealing with undefined behavior, is simply going to ignore it. It's simply going to say, well, I don't have to write any code for undefined behavior, so in the undefined behavior case, I'll just ignore that and write the code that works as if that didn't happen. But that's not actually how compiler writers think about undefined behavior. They could, and if they did that, they would create compliant compilers that would generate compliant code. But that isn't how they think about it. And why? Because most compiler writers are not trying to write compliant code only. They're trying to write optimal compliant code. And it turns out that the optimal way to think about undefined behavior is to assume that it never happens. Now, why is that different than just ignoring it? Well, the reason is because it turns out that you can make certain assumptions. If you're assuming that undefined behavior doesn't happen, you can make certain assumptions about your code that allow them to write tighter, cleaner, faster code. Now notice, this is still a compliant approach, because if they are wrong, and they're going to be wrong, right? People are going to have buggy code. Sometimes undefined behavior happens. But in that case, it doesn't matter what code they generate. So again, it is a safe, compliant assumption for them to make. So what this means is that if you are thinking, well, I know what will happen in the undefined behavior case and I'm good with that, you may be surprised. So let's take a look at this particular implementation of div except, which is it's division by 0. We throw an exception if there's division by 0. So the question is, are we ever going to have this throw? So it's ever going to be thrown? Some of you are jumping to the conclusion that you know what's going to happen in the undefined behavior case. In undefined behavior, anything could happen. So it could be thrown, but it won't be thrown. You guys are all right. It won't be thrown. Why not? Well, it's because the compiler is going to completely ignore the test on line 6, because the only way this could be true is if we had undefined behavior on line 5. And the compiler writer assumes no undefined behavior, and therefore can completely remove this. So you see the difference between ignoring undefined behavior. If the compiler ignored undefined behavior, then they would go ahead and generate the code on line 6. They're not ignoring it. They're assuming it doesn't happen. And if you're assuming no undefined behavior, then there's no point in writing line 6. So line 6 would be executed only if undefined behavior happens on line 5. Everybody see that? All right. So the lesson here, the moral of this, is not that you can't outsmart the compiler. The moral is that undefined behavior is wrong, no exceptions. Did you get that? All right.
On that note, say that you launched an object. So the idea is that you don't want to try access an object. It's not all uninitialized. So I would defensively go if objects or objects not equal to null. But so I'm seeing that happen blatantly well. What about would the compiler optimize that away in release or?
So this is actually a real world famous thing that happened in Linux, right? There was a call that you pass a pointer in, and it's legal to pass in a null pointer. That was legal in the definition of the function. In certain cases, we'll pass in a null pointer. And so there was a null pointer check, because obviously if you pass in a real pointer to something, then we do something with it. And if we don't, then we don't do the thing. What happened was someone added some code to do some kind of troubleshooting. And what they did was they added code to print out what was being pointed to. And they added that before the null check. So the compiler generated the code without the null check, because already undefined behavior had happened. This got people in the Linux world very upset. They said, you don't take out our null checks under any circumstances. But the compiler writers were saying, don't write undefined behavior under any circumstances. They actually kind of lost. There's now a flag for GCC that says, don't take out null checks. But really, it was because of undefined behavior. It was because the compiler was doing the right thing. Does that answer your question?
So essentially, it's because in that instance, the undefined behavior hashing before. Right, and if you look at was defined behavior or was checking for defined behavior. Right.
If you look at the code, the way I wrote this, I do the test after you've already done the right. Most people probably wouldn't have written it that way anyway, but I wanted to demonstrate this. Most people would have write this by doing the check first, and then the throw, and if not, then go ahead. You know, I mean, I wrote it in this way to demonstrate this problem. And that was what was the problem with the Linux, is somebody had added this little chesting and they printed out what the pointer was pointing to without checking first to see if it was null, right? So that was the issue there. But anyway, so and just a little bit about undefined behavior on that, because we talk a little bit in this class or in this talk about undefined behavior. So I wanted to talk about that. All right. So I've been making the point that we live with trade-offs in C++. A lot of different trade-offs, by the way, complexity trade-offs, a lot of trade-offs, but we also live with safety trade-offs. We're going for uncompromised performance, and that means, and I think I've demonstrated why, that means we make these safety trade-offs. So you might come to the conclusion that C++ is unsafe, and certainly a lot of people have said that. But I think making this claim kind of fails to understand how applications are developed. It rests on the idea, which is trivially true, that compilers produce the code we run. That is true. But the deeper truth is that applications are produced not just by C++ compilers, but by the C++ ecosystem. What do I mean by that? Well, compilers and the language definition are an important part of creating applications, no question about that. But so is tooling, testing, documentation, the availability of high quality libraries, training resources, language culture, and most importantly of all, programmers, right? And the C++ ecosystem has always been hyper aware of memory safety issues. We are well aware that we make these safety trade-offs, right? And so it's an important part of our language culture. It's reflected in the work the Standards Committee does. Each release of the standard of the language finds new ways for us to be memory safe without compromising performance, right? We have a lot of people thinking about this issue as much as we can, thinking about how can we make this safer without compromising performance, because I pretty much can guarantee you go to the Standards Committee and say, hey, I've got this thing. It makes things safer and it doesn't provide any performance compromise. They're going to take a hard look at that. They're going to like that. Right. All right. So that believing that safety is the sole responsibility of the compiler, I think, is to misunderstand the application building process. And it's likely to result in misguided attempts to build in safety at the cost of performance. I think this is self-defeating in part because performance itself is a component of safety. Applications that are more responsive to changes in the real world are going to be safer than those that have sluggish responses. All right, further, a logic error in a safe language is just as fatal as a logic error in a unsafe language, right? The real villains here are logic errors. It's the mistakes we make in our coding, irrespective of these kinds of trade-offs. So belief that a memory-safe language precludes the creation of buggy applications is a false sense of security that could get people killed. Imagine this all too likely scenario of a manager that mandates some trendy new memory-safe language that is so new that it doesn't have a ready pool of experienced developers, a well-developed culture, training resources, who then skimps on the tooling to detect bugs with static analysis, or on training so that the development team doesn't use or understand valuable techniques like programming by contract. The likely result is going to be expensive, buggy software with poor performance. Experience has shown that C++ applications developed by well-trained engineers using state-of-the-art tools and techniques will have better performance and be as safe or safer than applications developed in languages with a less robust ecosystem. The industry investment in C++ means that not only will these applications have performance advantage, but they're likely to also have a development cost advantage. Mandating that safety be built into the language definition is no guarantee of a safer final application, but it's pretty much a guarantee of mistaken performance trade-offs. So C++ has been and remains a valuable development tool due to its robust ecosystem and its high performance standard. So when modern C++, C++11 shipped, which is sometimes called modern, we introduce move semantics and R-value references. This is a major complication for the definition of C++. And I make my living teaching modern C++, and I can assure you that this is one of the most difficult single concepts. Am I wrong, Klaus? Most difficult single concepts for people to get their heads around, and that's true for novices, but it's also true for experienced C++ programmers, right? So including this move semantics got us what? It gets us fewer unnecessary copies, pure performance win. It also got us perfect forwarding, probably not quite as important, but it also gets us that. So why did we go to this extreme length just to get some performance of unnecessary copies? Why did we add this cognitive load to us as developers for that performance gain? Should be an easy question. Because this is C++, right? All right, all right. So we did this because we will do what we need to do to get uncompromised performance. So I want to take a look at a specific example of move semantics. So what we have here is a constructor that is move initializing a data member as opposed to making what could be an expensive copy. Let me see what's going on here, right? We have this type that has a data member of a list, and we can move into that list, into that data member, as opposed to making a copy, assuming assuming that an R value reference exists. All right. So what do we know about the list move constructor? Is it constant time operation? No?
Oh, sorry.
The move constructor. Yeah, I think that is constant time. Is it inexpensive? Is it non-throwing?
It has to be.
All right. So let's take a look at vector. The vector move operation, and by the way, move operation should be cheap, constant time, and non-throwing. And in fact, vector is. Vector is guaranteed to do no accept, it's constant time, it's going to be cheap. But notice move, or excuse me, list. List is not no accept. List is not no accept. Now, why is this? Well, because in my opinion, the committee's made a mistake and compromised our uncompromised performance. Let's step back and do a quick review now of move semantics. All right, so for this part of the talk, I want to assume that we're not using legacy types that don't have moves, and we're not using any data members that can't be moved, like const or references arrays. So let's just talk about types that are built up of these fairly simple types. So if we have that, and if we have source so we can go in and add move operations to everything, then we can make our types all move operations that are cheap, constant time, and no accept. If we follow this simple set of rules, which is for all our primitive types, including non-owning pointers, we just make a shallow copy. If it's an owning pointer, we do the shallow copy of the pointer, and then we zero out the source, because the source of our move no longer owns the resource. And then for compound types, we just use the move operations that we make by doing the same thing recursively. Okay, everybody see this? Okay, great. All right. Now, is this all we need to do to make our moves to move enable our type? Well, it turns out there's one other thing we may need to do. Probably destructors are going to be safe here, but we do need to make certain that the destructor code doesn't make any assumptions that isn't true for move from objects. All right, does that now make our objects movable? And those of you that are really clever will understand there's room still on the screen. What's that? Assignment, that's right. There's one other operation we need to support, and that is assignment. Now, why do we need to support assignment? Well, it turns out this is a very important use case, because it is very common in our algorithms that we will move a value from an element in a range, we'll move that so that a new value can be placed in that place, right? And when do we do this? Well, we do this for sorting, inserting, removing, uniquing, all of those things. If we have random access range, this is really important because, what's that? Right, but swap is based on moves.
Yeah, it needs the second operator on the move from object.
Oh, you're saying in addition to all those things, std swap needs, yes. Yeah, exactly. Or iter swap, yeah. We need that assigned to operation as well. All right, so these are the two cases that we need to be able to support, destruction and assignment. And they were identified in the first proposal for move semantics, which is those who paying attention at home, N1377 by Hinnett, Dimov, and Abrahams, our keynote speaker, Dave Abrahams, which described leaving move from objects in a state that is, quote, a self-consistent state. Parenthetically, it added, all internal variants are still intact. Now, in practice, many users took this to mean valid for destruction and assigning to. Now, no other operations were identified as needing to be supported, but that is not the actual wording of the proposal, because the proposal said all invariants are still intact. But in practice, all we needed was these two, assignment and destruction. So I want to note in passing that these are the exact two operations that are supported for uninitialized primitive types. Assigning to and destruction. So in other words, this interpretation that some people had was exactly what Alex Stepanoff and Paul McJones identified as partially formed objects. Right? It's exactly the same as an uninitialized object. The only thing it's safe to do is give it a value or just let it go. And those two things have to be safe. All right. Now let's return to vector and list and the mistake that I think that the standard library made, or the standard committee made in the standard library. The standard says that objects of type defined in the standard library, when moved from, are in an unspecified but valid state, and further they define valid as supporting any operation that would have no precondition. In other words, these are what Alex and Paul would call fully formed objects. Now, let's look at the implication of this for vector. Now, the standard doesn't say how vector is implemented, but it's an allocated array. So we can determine that we need 3 data members, right? I think we talked about this in the previous session. What are those 3 data members going to be? Pointer to the allocation, the array, yeah, and a size and capacity. Now, the size and capacity could be implemented with indexes. It could be an integer, or it could be a pointer. It could be implemented either way. Either way, what I'm about to tell you, doesn't matter how you implement it. Basically, let's take a look at an array of integers, or excuse me, a vector of integers. This is the data members for this vector, right? We're pointing to some allocation. What's the size of the allocation? What's the size in bytes? Times size of int, right? Whatever that is, that's how much it is. And how many integers are in? 10. Great, okay. So we're gonna move from this vector. Now let's apply the rules that we talked about earlier. The uncompromising performance for the least expensive possible move. That leaves us what? That leaves us this. The 10 and 16 are copied, so is the pointer, but after we copy the pointer, we go back and we zero it out, okay? This is the minimum possible work done to do a move from a vector. And if all we're going to do is destroy the vector or assign a new value to it, this is acceptable. It would work. But that's not what the standard says, right? This is problematic for the standard. Why? Because the standard says that you could call size, and if size is greater than 0, you could, for example, call front. And what does front do? Returns a reference to the first item. This is undefined behavior. We'll all see that, right? So what that means is that it is impossible using the standard library's definition of a move from vector object to implement it with uncompromising performance. You have to do some extra work. Now, somebody might argue and say, well, you could make the move as cheap as possible. You just have to make sure that size does the right thing by checking. But nobody would make that argument because it's not just size. It would be every single member of vector would first have to check to see if I'm in a move from state to do whatever it is. So the cheap and obvious thing, if you're going to have to do this, is to fix it in the move operation. So you're going to have to zero out size and capacity, right? Now, how much work is that? That's probably not a big deal. For vector, it's non-zero, but it might be more for other things. And in fact, that's the issue that we get into when we talk about list, right? It turns out that one of the major library providers for the standard library implemented list. In fact, all the node-based objects implemented them using Sentinel nodes. So a Sentinel node, according to Wikipedia, is a specifically designated node used with linked lists and trees as a traversal path terminator. In other words, if I'm going through my linked list or I'm going through a map, then I know that I'm at the end, not because something points to nil or something I don't have to check that. It's just a special Sentinel node that says you're now at the end. Now, I'm not going to take a position on is this a good idea. It's an engineering choice, and all engineering choice have trade-offs. There's some advantages to using Sentinels, there's some disadvantages. But one of the implications of using Sentinels is that we're going to have to allocate a node when we create our container, and of course we'll have to free that node when we free the container. It's no big deal, we only need one. We create it in the constructor, we release it in the destructor, we don't have to worry about it. Unless we do a move. So if I'm doing a move construction, then I need to have a Sentinel in the item I'm moving to. And it's no problem, the item I'm moving from has a Sentinel. So I can just move it. And that's fine if the only thing we have to do with the source is delete it or assign to it. It's fine if it doesn't have a Sentinel. But what if you have to be able to do anything? It has to remain a fully formed object according to the standard. So that means, yeah, you can move the Sentinel, but you have to create one to replace it. Do you see now why the standards committee said that the list move constructor is not no accept? It's still constant time, but it's not cheap, and it's not no accept. All right. Now, you might ask yourself, given this particular set of problems in the move case, why is it that a library implementer chose to use Sentinel? Well, as I said, there's trade-offs. There's advantages to using Sentinel. I've given you the bad side, but there's good sides too. But more importantly, when this decision was made, moves were not even proposed. This is a very old decision made a long time ago. So now the obvious question is, well, why don't they just switch? But the problem is this breaks ABI. It's a non-trivial ask to have a working implementation with literally, hundreds of uses and thousands of applications shipped, and now we're going to say you need to rewrite this entire library. Yeah.
They did that for string. It was a massive nightmare for them.
GCC rewrote their string implementation because they were using copy on write for the string implementation. And I think most of the issues with that are behind us, but it literally was a 10-year pain. It is a very much non-trivial problem to solve. And so rather than put someone through that, the standards committee more or less said, oh, yeah, we're not going to make this move operation be no accept. I think the better solution would have been for the committee to have said, look, if it's moved from, it's no longer a fully formed object. That's my argument, but that's not where we are. So here's what I argue. The additional cost of performance for vector, that's pretty much negligible. You're zeroing out two integers, right? I mean, 2 words assigned to 0. You might not even be able to measure it. It might be hard even to measure that. It's so small. Now, not true for list. List is more expensive. In fact, any of the node-based containers, that's going to be more expensive. But that's not my real objection. My real objection is that I feel like the standards committee is encouraging people to make logic errors. Why is that? Because I believe that if you're asking an object its state after it's been moved from, that's a logic error. If you need to know the state of an object, you should not have moved from it first. Right? See my point? Yeah.
I thought I might miss. So what was the house state for not doing that? I don't understand why.
So there is a reason, and I will get to it. I want to make their argument. There is a good reason. I don't think it's good enough, but there is a reason for it. Let's get to that. But I want to point out that this is what the standard library has done. The standard library has said if it's in the standard library, it's fully formed. You can move from it. And then after moving from it, you can say, well, by the way, what size are you or what your state? And I think allowing people to do that, documenting that, is a logic error because you're telling people the wrong thing. This isn't actually in my notes, but it is in my notes that I talked to Howard Hinnett about this talk. He actually caught an error in the talk when I sent him the notes. He said, no, that's not true. So I fixed it. But one of the things as we were talking, and I'll talk about his solution, which is different from mine. And I pointed out the issue with his solution as opposed to mine is that it's much harder to teach. I said, what we want to do is we want to teach people that a move from object is a partially formed object. There's different approaches you can take, but they are more complicated, harder to understand, you have more exceptions. It's better to just teach people. Because it's easier to understand and it works. There's no situation where you want to move from something and say, by the way, what is your state? That's just, as I say, it's a logic error. You shouldn't be doing that. All right. Now this is in my notes, and that is that maybe I'm wrong. Maybe there's something else you need to do with an object. You move from it, and instead of just assigning to it or destroying it, there's something else we need to do. And in fact, this was actually pointed out to me by a friend of mine who is a standard library implementer, who's a member of the standards committee. Not Howard, by the way. In my notes, one of the things Howard said is, you're misquoting me. I didn't say that. And I said, no, that's not you. That's somebody else. Now, some of you think, probably, the way I talk about the standards committee, that I have no friends on the standards committee. Some of you think, because I talk incessantly about C++, that I probably have no friends at all, but that's not true. That's not true. Now, he's a friend of mine, and but I didn't ask his permission to use his name in the talk, so we're going to call him Inigo Montoya. Some of you may not get this joke because, anyway, some people know immediately who I'm talking about if I call him Inigo Montoya. All right, so I told Inigo that there are other use cases, that there are no other use cases for move from objects except destroying them or assigning to them. He said, well, no use case we've discovered yet. Okay, obviously I can't disagree with that. That's trivially true, but I will point out we've had move semantics for almost a decade and a half. We've created hundreds of algorithms, and we haven't found that use case yet. So I would argue it's unlikely at this point that we're going to discover that use case. But Inigo actually came up with his use case. He said, suppose I have a vector, and I populate it with a bunch of pushbacks, and then I move from it. But I'm in a loop. So after moving from it, I want to populate it with a bunch of pushbacks. But I don't want to have to, what would I have to do under my rules? Well, we'd have to assign an empty vector into it, right? Which is trivial to do. Single line, very inexpensive for the, no memory has to be allocated. We can do that very cheaply. But he doesn't want to do that. He said, I just want to push back and then move. So I point out a couple of problems with that. The first problem is, of course, he's making an unfounded assumption. He's assuming that once he moves from the vector, it's empty. Well, he's a standard library implementer. He knows it's going to be empty, but the standard doesn't say that. Standard says it's in some unspecified state. But also, although it's a little bit cheaper for him to not make the call to initialize this, the cost of making every move ready, truly zeroing out the vector every time is more cost than the performance of him doing that right inside this loop. So technically what he's saying is true, but I don't think it's a strong argument. I don't think it's very compelling at all.
Could that be resolved by changing the way you do the move rather than using vectors by moving individual elements? Just would keep the memory there, so you could then use it as like a vector that has been moved from, but still be fully formed and usable.
Well, my assumption is in his example, when he did the move from the vector, he wanted the buffer that all the items were in to make that as cheap as possible. And then the from vector, he knows it's empty. It's just not documented to be empty, is my point. All right. So why did the committee make this decision? In response to your question, well, I understand why library implementers want this rule. And it's because, we have a name for invariants that don't always hold. What do we call invariants that don't always hold? What? Bugs. Variants that don't always hold are called not invariants. Right? The whole point of invariants is that they always hold. So from a library implementer's point of view, they get very itchy, uncomfortable when you say, oh, well, we've got this object, this type we're defining, it has these invariants, but when it's moved from, those invariants don't hold anymore. They get uncomfortable with that, and I understand that. And I don't want to weaken invariance very much. I don't want to weaken invariance. But notice, invariants already don't always hold. Suppose I have an item on the stack, and I call the destructor on that item. Can I now call member functions on this? No, of course not. I can't do that. The invariants don't hold anymore. Why? Well, the item's lifetime has ended. But I think that's how we should think about move from objects. Their lifetime, it's not truly ended because they can be assigned to, but their lifetime is suspended. They're in suspended animation. They are in the same state as an uninitialized int, right? They have a type, they can be assigned to, they can be destroyed, but those are the only operations we want to do. It's in a suspended state. And I understand why that makes library implementers uncomfortable, but if our goal is uncompromised performance, that's what we're looking at. Now, there's also another reason. And the clue to that, I think, comes in Herb Sutter's blog. So back in February of 20, he wrote a blog post called Move Simply. And in this, he explains that move from objects of well-defined, well-behaved types need not be treated with any special restrictions. If it's a well-behaved type, according to Herb, then when it's moved from, it's still fully formed. You can do anything with it you want. Now, the reason that he did this, and I should say, when I teach classes, I don't teach this. I teach that if you move from an object, you can only assign to it or destroy it. And when I tell people this is your responsibility to track that on a move from object, you can feel the anxiety in the room go up. But then I immediately say, but that's not that hard. And the reason is this. You only move from an object if you know that you're about to destroy it or about to replace it. That's the only time you move. You wouldn't move from an object under any other circumstance. So there is a cognitive burden placed on you when you do a move. Now, for those of you who haven't caught, the only way to do a move, we're talking about when you actually say std move of this. If you're doing an assignment from a temporary or something like that, that object doesn't exist anymore, you don't need to worry about it. This is an issue only when, in your code, you actually type in std move from this object. When you do that, it's now a burden on you to make certain that the only thing you do with that thing that was moved from is to allow it to go out of scope or assign a new value. And I think the motive that Herb has is he wants you to not have that burden. He wants you to say, well, sure, I moved from it, but I can still use it as any other object. It's still fully formed. And that is, believe me, from a training point of view, that's nice. To just say, yeah, it's moved from. We don't know what value it has, but it has a value. You can use it any way you want. You can ask it what its value is. But I think when we do this, we're introducing a logic error, because to say, yeah, I can move from it and then I can ask it what its value is. Its value is unspecified. There's nothing important about its value. If there was, we wouldn't have moved from it, right? Okay, so I want to point out, I'm going to be criticizing Herb's position. I want to make it really clear that I consider Herb a friend. He's also my boss. Herb is the president of the Standard C++ Foundation, and that puts on cppcon that I am the conference chair of. Herb is literally my boss. And I have great respect for his contribution to the C++ community, and for him personally. I've got all his books. I've read them all a couple times. I have great respect for Herb. I disagree with him on this issue, but it's not personal, it's entirely a technical disagreement. And I want to make certain everybody understands that. I am not Herb's enemy. So, in the blog, he refers to these well-behaved types. In other words, these are types that even when moved from, still have all of their invariants are still there. Now the thing is, the reason he says that is because the standards committee can't mandate how we write our classes. We do what we want. Our design of our classes, that's fine. They can't mandate that, except kind of they can. Why? Because if the standards committee says any item passed into the standard library must meet these requirements, well, who's going to write a type that you can't put into vector? Or you can't do a sort? Or you can't put it on a thread, right? Of course, if the standard library says types must behave this way, they're pretty much telling us what we have to do. But Herb is saying if it's a well-defined type. All right. Now here's the issue. If you read this blog, be absolutely certain to read the comments, because Sean Parent pointed out something in the comments. There's a couple of places in the standard that have these notes. You see the note here. So what's a note? Well, a note in the standard is called non-normative. And what that means is this note is trying to explain something, but the note itself is not part of the standard. Obviously, it's published as part of the standard, so in that sense it is. But the note is not considered to be what the standard says. It is an explanation or an attempt to explain what the standard says. So in this particular case, what's happening is what the note is saying is if you have something that's passed into an algorithm that accepts movable things, that the thing when moved from, so the expression that RV, it's a temporary, is being moved from, then down in the note, it says the operations listed in the requirements must work as specified whether RV has been moved from or not. So in other words, if we're putting something in the standard library and the standard says this thing needs to be able to do this, then if the algorithm moves from it, it still has to be able to do that. Now, here's Sean's example of why this is problematic. So Sean looks at this and says, okay, so we have this array of unique ints, and I want to sort my array. Now, if we didn't pass in a comparator, how would this be sorted? What would be the criterion for sorting it? How would it be sorted? It would use less, but less of what? Is it going to figure out that 0 should come before 1? No. What's it going to compare? The pointer value, right? Which is not what we want. We want the integer value. And so we give it a comparator. And the comparator in this case is a lambda expression to dereference the items in the container and compare what they point to. Is this going to work? Is there a problem with this? I sure hope Sean isn't writing code that won't work, right? Right? Is there a situation where we might try to compare one of these objects when it's moved from? Is the sort going to move from these objects? Is sort going to move from these? Notice he deliberately created these in the wrong order, so they're going to be swapped, right? That's what sort's going to do. It's going to swap the order of these two items. So is it going to do it by copy? No, it can't. Unique pointer. It's going to do a move. So there will be, inside the sort, there will be instances when the items are moved from. They're in a moved from state. When in the moved from state is the algorithm, the sort algorithm, ever going to use the comparator when they're moved from? Not if sort's written properly, right? You're going to do comparisons, and then you're going to do a swap, and then you're going to do a compare, and then you're going to do a swap. That's how all sorts work, right? So that's what Sean's saying is this is absolutely rock-on code. But notice it doesn't meet the note that's published in the standard, because the standard says that you have to be able to give it a comparator that can work on elements in your range, but then the note says even if the elements in the range are moved from, the comparator still has to work. So technically, in order for this to meet the requirement of the note, Sean's comparator would have to check for the case of the object being moved from. But that would never ever happen with a properly written sort. So we see the issue? So we have a question? Okay. This is what, yeah. if this was moved from when we did it, it would be undefined behavior. But a properly written sort is never, ever going to apply. Why would you? What difference does it make what its value is when moved from, right? The only reason we move from it, thank you. The only reason we move from it is to be able to do the swap. All right, so this is what Sean says that the note should say. It should say that the item is assignable to and destructible, otherwise no state is the state is unspecified. So what I'm thinking is that Herb's blog has created this illusion of safety. He's saying that if you call this member function on you can call a member function on a move from object and it's not going to crash. That has to work. But notice, it's in an unspecified state. It's not going to do anything useful. It's just not going to crash. But if calling it is a logic error, then that means we've got a problem somewhere else. We've got a design problem. That somehow we're thinking, oh, I'm going to move from this and then I'm going to figure out what its state is. That's a design problem. That is a bigger bug. So we got rid of the little bug. You can actually call this function and it won't crash immediately, but probably your application is going to crash or behave badly in some other way later on. All right. So as I mentioned earlier, I was able to reach out to both Howard and Sean in talking about, I showed them my notes and got some feedback from them. Sean not only identified this, but he thinks there's a bigger problem, and he gave this talk called "Warning: Standard Find is Broken," which is kind of related to this, but on a bigger issue. He's pointing out there's problems in the way that standard is defining algorithms, and that fixing this is only part of fixing a bigger problem. You can read more about this with this particular paper, and Howard is pledged to help him work with this. Now, Howard's position is a little bit different than mine. Howard doesn't want to tell us how to design our move from objects. What he's saying is, what we should do is we should look at every single algorithm and very carefully vet what its requirements are. And I'm all for that, because there's no algorithm that's ever going to say, by the way, if this object's moved from, it still has to, no, never going to say that. All it's ever going to say is that exactly what Sean's comment was. Sean's comment is that it's got to be destructible and it's got to be assignable, but nothing else has to work. And so I'm all about Howard. Now, to point out what Howard wants to do is he wants to be able to support a situation where, let's say you have a vector and some of the items are moved from, you'd like to be able to sort them with the move from items, and the sort function should still behave properly. And I'm all for that, but I still believe that if you are moving from something and not immediately destroying it, that's a logic error. Well, again, Howard's more open to that. He says, well, that's not my problem. I write the library, and I want to document the library to say, even if items in your range are moved from, as long as your comparator supports move from objects, we still should be able to compare that and sort that, which, okay. Yeah, okay, so let's see. So I want to consider the semantics. What I mean, this is the meaning of these two signatures. So what does the first signature mean? The first signature is saying that this function is free to modify the passed in item as long as it leaves it in a fully formed state. All the invariants have to be intact. That's what the first signature. Everybody agree with that? But what does the second signature mean? Well, one possibility is that the second signature says that the function is free to do anything it wants with the passed in item, but it has to leave it in a state that it can be assigned to or destroyed, but no other item. Or it could mean the exact same thing as the previous signature. Those are the two options. Either you do it the way I think you should do it, which is to leave an item in a partially formed state, or basically these two signatures mean the same thing. That's what Herb's blog is saying. That these two signatures actually have the same semantic meaning. All right. I want to give you one final example, and I think this is, for me, this is a killer example because we're talking about undefined behavior about uncompromised performance. So imagine that we have some OS, and in this OS, we have some ability to call down and create some magic viewport, and this is color, three-dimensional animation driven by an AI model, and it's this magic thing that is just huge and wonderful. But it's expensive to create. When we call create viewport, that's an expensive call. Okay? And then once you create that, you get this viewport ID, which is probably a pointer or maybe an index, and we can pass that into a bunch of OS calls to get and set properties on our viewport. Okay, so everybody see what I'm doing? Now, those of you who are C++ programmers, which I assume was all of you, are immediately saying, this should be wrapped in a C++ object, right? Hope you're all thinking that. All right, so here's my C++ object. The data member is the ID. Hang on here, let's get this in sync with my notes. The data member is the ID. Notice I just put a comment inside the constructor, but to be RAI compliant, if we call create viewport and it returns null, then that means it didn't get created. We should throw an exception. We should be RAI compliant, right? But other than that, this is good math. Now, we want to have now a bunch of getters and setters. We're going to call down into the OS and pass in the viewport ID. Everybody see what we're doing here? Okay. Now the question is, how do we handle move operations for this? Now I think what we should do is we should shallow copy that ID that the OS has given us, which is, as I said, either an integer or a pointer. We copy that to the sink, to the item being moved into, and then we zero out that on the from side. Now, will the destructor work? Sure, the destructor is going to work. We can assign a new value to it. But what about all the other members? Well, in my world, you never use those other members. Those are logic errors. But if we're going to follow Herb's advice, we have two choices. One is we could do this part, but then what we need to do is make a new viewport to replace the one that we gave away so that we can call in and make all those other member functions work. Now, does everybody see that this kind of ruined the whole point of move semantics, right? The whole point of move semantics was that it was cheap and easy to just move that ID over. But now we're going to turn around and we're going to create a new viewport on an item that's going to be destroyed, right? And we don't even know what parameter, we just have to create one so that all those member functions are going to still work even though they're kind of useless. So that's one solution. There's another solution we could do, and that is we could leave it in a zero state, not make a new one, but we could modify all the member functions to create some fake thing to pretend like we actually have a viewport. Do you see what I'm talking about? Right? Now, what are the implications of this? Well, one of the implications of this is that we've compromised our invariant. What was the invariant of the class? The invariant of the class was that if this class exists, you have a viewport. Because remember, if we didn't get the viewport, it threw an exception. So if the class exists, you have a viewport. That's the invariant. Now the invariant is, if the class exists, you have a viewport or you don't. Right? The most important single invariant of the class has just gone away. Plus, now we have a whole bunch of member functions we have to create that check for a state, move from, so even in the non-move from state, we have this overhead where we first have to check, say, well, have I been moved from? And if not, then I have to do something. And if I have been moved from, then I have to do something that's safe but useless. You see the issue? We got two possible ways to implement this to be consistent with the blog post. One is to completely ruin the whole point of moves. It's no longer efficient, no longer uncompromised performance. And the other is to basically ignore our most important invariant and then do a whole bunch of stuff that has to be tested and documented and a lot of waste, I think, right? Any questions about that? All right, I want to summarize my main points. So, what is C++? I think C++ is about uncompromised performance. That's the reason this particular language exists. It's not unique. C does the same thing. But that's what C++ is about. The difference between C and C++ is, yes, we also support, as you said, we support that high-level reasoning that C doesn't support. That's terrific. But we never compromise the uncompromised performance. And this is achieved by living with undefined behavior, accepting the safeties. There's other trade-offs too, but the one I focused on was this. Also, the committee is saying that standard types move from objects means fully formed. That ship has sailed. I think it's a mistake, but it's a mistake we can't correct at this point. It has a minor performance on almost everything and a major performance hit on some things. If you have Sentinels and maybe other cases too that we don't know about. And I think more importantly, it leads to logic errors. The committee's direction is that user code move from means fully formed. I think that the motivation for this is that it makes, it's a cognitive load. It says, oh, you don't have to worry if it's moved from. You can still do whatever you want with it. I don't think that's a good idea. I think it leads to logic errors. And in some cases, particularly one I just outlined, it has either unacceptable performance or it defeats the point of movement. I think the correct way to think about move from objects is as partially formed objects. The only thing we'll do from them is either assign to them and destroy them, and that's it. Oh, I forgot to ask. Why do we do, never mind. And then there's one other thing I want to talk about, and that is that I don't think that language safety means application safety. I don't think those are quite the same thing. We have I think that the C++ ecosystem is this rich culture about both performance and safety. We're very, very concerned about safety. Every new version of the standard has more ways of being safe without compromising performance. C++ is high performance, but I believe that C++ is also safe. I believe that C++ is evolving to be better in these areas and other areas. I think we can have it both ways. We can build safe applications with uncompromised performance. And how can we do that? How can we do that? Because this is C++. All right. Thank you guys very much.